remainders, we have this division statement, and this division statement is very important. Okay, so we can see the factor part pieces here and a remainder piece. If the remainder is 0, that's great, because then we're only dealing with these factor pieces. Now there's different rearrangements of this division statement. This is a multiplication form of the division statement. We could have the division form of this division statement as well. Okay, typically this is much easier to use, so we don't necessarily use this form unless we need to. Now this division statement can accommodate multiple divisors. We did this in a problem the other day as well. So we had these two divisors here, and we can just write it as well. Just keep those divisors together. That's part of the factor part, and we're still going to have this r of x. And we can express it in the divide form with both divisors, or we could even express this divide with just one divisor. Okay, and that means that if we divide by both factors, we're left with the quotient, the answer to the division, plus the remainder of the divisors. Or if we just show it with one divisor, we keep the other divisor with the quotient, and then we have the remainder over one divisor. Okay, so here's a problem, similar problem that we did the other day. So we have this unknown p of x, and we divide it by 2x squared plus 3x plus 1. Now, the remainder is 3x plus 2, and we want to know the remainder when it's divided by these individual factors, x plus 1, x plus 2. Now, first of all, it's important to recognize that when we combine these two linear factors, we end up with this factor here. So I'm going to write the division statement out. I have my p of x, unknown, is equal to my q of x. Okay, actually I should do this in green. My q of x I usually write in red, so my q of x, unknown. But I do have my d of x, okay, which are these two pieces. So I'm going to write it like this: x plus 1, 2x plus 1, and then plus the remainder, which is 3x plus 2. So how do I solve this problem? How do I know the remainder when I divide by just x plus 1 and just x plus 2? Well, we can kind of look at it this way. In fact, we can use the remainder theorem. If I plug in p of x, for example, p negative 1, that will give me the remainder when I divide by x plus 1. What does p negative 1 look like? It's going to be q of negative 1. Okay, so q of negative 1, unknown. We have no idea what that is. However, the nice thing about this is, when I plug it into here, that's a 0. I've now generated 0 as a multiplier. That's great, because that gets rid of all of that. So even though this gives me some number, gives me like negative 1, it doesn't matter. This whole expression is equal to 0. This is now equal to 0. And that just leaves me with the remainder term. Okay, so I can have 3 times negative 1 plus 2, and that's whatever this p of negative 1 equals, that's my remainder. Well, the only thing that's going to be left is the remainder. So it's going to be negative 1. So my remainder is negative 1 when I divide by x plus 1. When I divide by divide by 2x plus 1, I'm going to be plugging in negative 1/2. And again, I don't know what q is, so I don't know what q of negative 1/2 is. That's unknown to me. I don't know well, I do know that negative 1/2 plus 1 is positive 1/2. But when I plug it into here, I now generate a 0. So again, I've generated a 0. All of this is equal to 0. So then the remaining piece plus 3 times negative 1/2 plus 2, that must be my remainder. So I end up with negative 3 over 2 plus 2 is positive 1 over 2. So that becomes my remainder. So that's one way I can look at this problem. Okay, I can think of it as use the remainder theorem to do this. The other way, it's asked to show two ways, so another way I can do this, and I'm going to do this, draw a line here, and this is method number 2. Okay, we'll call that method number 1. The other way is to do this. We can just do some reasoning and say, if I divide this and I get this remainder, this means that everything on this side is divisible, evenly divisible by x plus 1, x plus 2. That means that this here is not necessarily divisible by x plus 1, x plus 2. In fact, it's not, otherwise it wouldn't be a remainder. So if I wanted to get the remainder, I can just divide by that I can divide one of these by the 3x plus 2. So I'll show you what this looks like. Okay, so we can rewrite this using an alternative form of the division statement. So it's going to look like this. Q of x, again unknown, Q of x times, okay, I'm going to divide by x plus 1. So I'm going to go divided by x plus 1, divide by x plus 1. Well, that's going to end up just canceling the x plus 1 out. So I'm just left with x plus 2x plus 1, okay, plus, this is going to be 3x plus 2, divided by x plus 1. Okay, well this doesn't create a remainder term because when I divide I get this whole piece. Okay, so all I really want to know is what's the remainder when I divide this. So to get the remainder, okay, the answer, remember, was -1. I'm just going to divide x plus 1 into the 3x plus 2. And when I do that, I'm going to end up with 3. I'm going to go in there 3 times, and I'm going to have a remainder of -1. Okay, which is consistent with what I got that way. And notice that if I divide the 3x plus 2 with the other factor, okay, 2x plus 1, I'm going to get 1.5. So that's going to be 3x plus 1.5. Subtract that, I get 1/2. That's my remainder. And again, notice how that's consistent with what that is too. So these are two different ways we can do this. It's probably easier to understand it through this division statement and being able to plug in and generate 0 factor here. But there are alternatives ways to look at this as well. It's to do with this polynomial divisibility.